All right, fine. So I'm gonna start off here. So our project was the deep learning computer vision, and pretty much what our goal was to do was to use a convolutional neural network to be able to identify and classify different images. No, we used to classify what was in the image. We'd say if it's an apple, if it's a sandwich, or whatever it might be. And on top of that, we also decided to do image segmentation, which is now that we know what the image is, we're also going to highlight where exactly in that image is the object we're looking for. So if we have like a plate with a broccoli, we're going to say that this is a picture of a broccoli, and we're also going to highlight the broccoli, saying that this is the broccoli. So yeah, next slide. So the way we were doing this is we were using so we all decided to stick with VS Code. So we all were using the same IDE. If we ever had any issues, we could easily troubleshoot it. We were also running our computers on Ubuntu using AWS servers, specifically using EC2 instances. The reason that was important is because we needed access to GPUs. So we use instances on Amazon. We would spin them up, and then we connect through Visual Studio Code to our instances, so we have access to GPU, and we could have everything was on the cloud, and all of our development was done in TensorFlow. So that's sort of like how we did everything. So now I guess we'll get into a little bit of the background of what we did. So just to go over quickly, these are courtesy of Gershom's slides, but basically what a convolutional this is. So a picture can be described as a 2D array. If it's a grayscale image, it's a 2D array of different values. So in this case, this is going to be values of the blacker part of the image is going to have higher values, and the lighter part of the image is going to have lower values. So in the image over here, you can see that this person's hair, I guess, on the left side it's black, on the right side it's lighter color, and you can see that represented in the values in the table on the right. That the darker the image, the higher the number is going to be. This is a kite. Yeah. Okay, sorry. So right. So this is just so that's the image of the 2D array. And what we're going to do is we can actually multiply that by what's called a kernel. And each kernel's got different attributes, but what's going to happen, go to the next slide, is that say we have different kernels. Say this is the vertical edge detector, horizontal edge detector, and we can pretty much take this original image and apply, and if we multiply every 3x3 pixel array set, we can actually come up with new images that have different aspects to them. So it's going to be a slightly smaller image, just because you can't get more than you can only multiply an area that's going to have 3, so you're going to lose the outer bound every single time. But you're going to have these different versions of these images, so you're going to have a lot more information about these images. And just to, I guess, make that a little more conceptual, so go to the next slide. So over here you have our original image in the gray on the left, and after applying our first set of kernels, we're going to end up a number of smaller images. And as you can see, as we said before, we have vertical line images. So on the bottom left, you can see different lines, different directions. So it's more information, but it doesn't really mean anything yet. But now on this new set of images that we made, you can apply more kernels and multiply it, and you're going to get more features. You'll see an eye, a nose, and eventually, keep doing this, you're going to get slightly smaller images, but it's going to be a lot deeper. So maybe the network's going to be able to recognize whether it's a face. So the deeper you go, the less resolution you have, but the more conceptual information the model might have. And so this is important because as you keep going, eventually you're going to end up by a 1x1, a 1D array of pretty much all this information. And once you have that, if you can actually scale that to whatever classes you have. So because as before, going from more abstract to less abstract, you have like just lines to a nose and ear to a face, and then eventually you can get to either the actual object you're looking for, a lion, horse, a dog, or in our case, we used fruits and other food items. So that's pretty much how the convolutional neural network works. So that's what we did. When we made it ourselves, it was around not so efficient, maybe 60% efficiency, but we can actually get that a lot more with TransferLink. So this is pretty much taking a different model that is trained on a lot more information, maybe millions and millions of photos. And this model could be used for a lot of different things and have 95% efficiency on, if it's a car, a truck, a bicycle, whatever that model is made for. So we don't have that many images. We only have like 60,000, something like that. So what we did is we actually took one of these networks that was designed for something bigger and made with a lot more images, and we took that and we actually cut the end off. What that means is pretty much now we're left with a base model that's good at sort of interpreting images, but doesn't really have an output. So what we can do is we can just say, hey, your output should be 10 classes because we have 10 objects that we want to classify. And now we have a model that's pretty good at seeing images, and we're saying it's going to be trained on our data. And therefore, it's able to get, in this case, it'll know if it's a car or a truck more easily. So with this, we're able to get, I think, 70% accuracy. So pretty good jump. But if you want to get even more, you have to do what's called fine tuning, which is pretty much instead of just changing the last cone, is you let the entire model retrain. And this way you can get even, instead of just having the last piece guided to our problem, we can guide the entire model to what we're trying to do. And with this, you can get up to 90 something percent efficiency. I forget what our peak was, probably 93, 94, maybe. But efficiency. So you can get very, very high numbers. And just a little bit more on that. In terms of choosing a base model, there are a lot of models out there. We personally stuck to EfficientNet B0 through B4. Most we did on B1, and you can see that there's a lot of different things to keep in mind. For example, EfficientNet B1 is only 31 megabytes large, so it's not super large, but it can still get fairly high accuracy and it has 7.9 million parameters. It's like a good. We thought that was a good starting point. Obviously, we won't want to do on something like EfficientNet B7, which is significantly larger and takes 61 milliseconds for like the GPU. They take forever. Even on B1, training on our data could take well over 10 hours. So we felt that EfficientNet B1 was a good balance between how long it takes to train and also the efficiency and what we can get from that. And just in terms
You were
of
doing the training on a single node, or you were trying to distribute the training across multiple nodes?
I don't really understand. What do you mean by node?
Were you training on one machine, or were
Yeah,
you? Okay, so there was okay, good.
yeah. And just in terms of of course having like just like percentage number isn't super isn't super easy. So these are actually real data that we had. We had training and validation actually that help us determine whether or not our model is plateauing. So if we know that's plateauing, it means that there's nothing else we can do. But if we can see that there's still a straight line, that there's still more. If we run our model for longer, more epochs, it'll actually continue to get better. So here you can also see I also drew the line of where fine tuning stopped and started. This was a pretty good run. I think we got looks like 90s, mid 90s. On top of that, it's also really important is generating a confusion matrix. So this really gives you an extra level of depth to the model. Because with this, you're able to see where your model's messing up. What a confusion matrix is what the picture was versus what the model thought the picture was. So you can really see where the model is tripping up. So theoretically, there should be a perfectly diagonal line where every thing the model thinks it is what the image is. But you can also see on this picture, it's a bit small for me, I can't really see, but towards the bottom middle, there's a square that's slightly higher up. So that's cake and pizza. So you can see that our model is having trouble differentiating between cake and pizza. That would signal that we should go back in the training data and see maybe our data is not so clean. And just more on figuring out data is any good. I think Jason's gonna walk us through how to make sure data was good.
Yeah. You wanna switch to the next slide? So what we did to make sure there's something called overfitting for models, where if you overfit your training data, basically the model would basically memorize the training data instead of learning it. So then we'd see very good performance on the training data set, but very poor performance on any new images that we gave our model. So we use data augmentation. So as you can see with the cat, with data augmentation, we basically transform each input image through cropping, flipping, and rotating. And then we save and add each of those images basically into our training data set. And then we use all those images for our training data. So that way our model is better able to generalize. Like for a picture of a cat, it would be able to generalize much better when it sees all those different versions of it. And it also increases our training data set size, which is one of the best ways to prevent overfitting to begin with. Next slide. So we also use the dropout layer. The dropout layer is another effective thing. The way it works is we give the dropout layer a probability, like 20%, and then it's basically saying to the network that 20% of the neurons from the previous layer let's not use for further learning. And basically doing this, we're forcing the model not to rely heavily on any single feature or neuron from the original image, since it can always be randomly dropped out. And instead, the model will have to learn more from other parts of the image. This also only applies to training and not the inference, since we want to use the full power of the model on inference. And this will also help our model's ability to generalize on new data and will improve our accuracy on testing. Next slide. So loss function was another important thing for improving accuracy. So first, the loss function, what it does is it basically tells our model how it performed using the prediction and truth values, and it goes into a function. So the model will try to adjust the weights inside the network to reduce our loss, which will give us better accuracy usually. So at first we use binary cross entropy. And binary cross entropy works well in most scenarios. If you look at the graph on the top right, you can see that it assigns some loss even when it's mostly correct, the predictions. So this didn't really work so well for us because we had very imbalanced data set. So the smaller classes were not having as large of an impact on our weights as the larger classes. So our model was getting really good at performing well on the classes where we had a lot of images, but it wasn't performing as well in the classes where we had less images. So once we switched to sigmoid focal loss, because sigmoid focal loss weighs more on the misclassified images, you can see it only really, when the images are really, really wrong, it'll affect the loss, and it ignores the correct predictions mostly. We saw an improvement on the accuracy of the underrepresented classes. Next slide, I guess. Tovia now.
Yeah, I'll take over. Okay, here's Zach, you take this. Yeah. Instance segmentation. Okay, so first of all, what is instance segmentation? That is where you identify which object each pixel in an image belongs to. Look at a pixel, is that part of a plum, part of an apple, part of a bowl? And yeah, that's it. Okay, next slide. Okay, to do instance segmentation, we use what's called the U-Net architecture. This is based off of the same concept as a convolutional neural network that Zach introduced above, in the sense that it performs a convolution on many convolutions on the image, scaling it down and passing it to a very high level representation of the image. And that's where you see kind of like the left side of this U. We call that the encoding process, or the downstack. We take the image, we boil it down to a very conceptual or high level representation of what's inside of it. Then we perform what's called decoding, and that's using a similar operation to on the image, on the data. We call a transpose convolution, which actually increases the size of the image, and we use that to build the image back up into a segmentation mask, which I'll show you quickly on the next slide. That's a segmentation mask is just an image that has one value for has like a different value, either 1, 2, or 3 for each different type of object within it. So in this case, you'll have 0 for background, and that's the purple, or 1 for broccoli, and that's the yellow. So let's go back to the previous slide. So that's what we're trying to accomplish with the upstack. That's the the right side of this U. We call that decoding. An important feature of this architecture happens in the encoding is what we call skip layers. Those are those little gray arrows going across the architecture. When you are building up the image again, if you were to just use the very abstract representation that we developed with the process, then we wouldn't have any information about the actual contents of the image. We just know that, okay, maybe this is like some sort of broccoli thing, or we don't know where in the image the broccoli is. So what we do is we provide at different levels of the coding process, we provide the model with information about the image at the corresponding level of the encoding process. So, for example, at the third layer from the top on the left side, there was some sort of representation of the image produced. And we passed that to the third layer from the top on the right side of the architecture. And this allows the architecture to make decisions based off of the actual contents of the image. All right, next slide. Okay, next one. Yeah, we chose to do segmentation only on broccoli objects out of the 10 classes we were doing. We decided to work on. We didn't really have enough time to develop this into like a segmentation model that works on multiple different types of objects. So this is what we got to.
So how did we go from just an image classification and segmentation model to something that can actually detect objects in an image and segment them? So in order to create the bounding boxes that we ran the image classification model on, we used a selective search algorithm. So the selective search algorithm works by using a superpixel algorithm, and it will then create bounding boxes based on those small sections, and then use the color of the different sections and the texture, which is basically texture similarity, which is basically takes 8 different Gaussian derivatives and runs them on each channel, and then with a histogram with it, which is and compares the intersection of those two histograms between the two different sections, and it'll also take into account the size of each section. So it will try to combine the size of smaller sections to avoid the problem where a big section will combine with smaller sections, and then you'll just end up with bounding boxes around that larger section. And also if the shape is compatible, so if two sections aren't touching each other, then they shouldn't get merged. So then you keep running that. So on each time you run it, you will create bounding boxes off of each time. So you'll continually get larger and larger bounding boxes. So that's how you get the bounding boxes. And then you run that through a model in order to figure out which bounding boxes correspond to which class. Next slide. But then the problem with that is you end up with thousands of bounding boxes, and you want it to be a much smaller number. So we use a non-maximum suppression algorithm, which takes the intersection over the union of the bounding boxes. So if the two bounding boxes, if the percentage of the intersection is within a certain amount, then it will get rid of one of the bounding boxes. It will get rid of the bounding box with that the model has a lower confidence in. And then we also use with the non-maximum suppression algorithm, that it will get rid of bounding boxes that doesn't have high confidence in, because you can end up with, let's say if you have an image with kale and broccoli, if there's a really small bounding box on the kale, it might think that's broccoli, but it has a low confidence in it, so you don't want to use that. Next slide. So how we went from object detection to also segmentation is we took the bounding boxes that we created for the broccoli, and then we ran those sections through our segmentation model. Next slide. So our model is very good at detecting broccoli, carrots, and bananas, but it has trouble with cakes and apples. So it can, next slide. So the model often confuses apples with oranges. So if you see on the image on the left, we have all the bounding boxes that the model predicted to be apples, and the one in the middle are the ones with oranges. So it's confusing. The model thinks that images that are apples are also oranges. So then when you run it with our which is limiting, bounding box doesn't have high confidence in, it ends up eliminating it ends up eliminating the apple bounding boxes. Next slide. So how can we improve? So because the food data set has a lot of overlapping images, overlapping objects, there aren't a lot of, we end up with very few apple images. So we need to supplement the COCO data set with something else. We should also try to get the segmentation to work on all 10 of our classes. And the segmentation model also has issues with, it will sometimes segment more than just the broccoli. So that can also be improved. Trivia.
Okay, generating the data sets. Okay, yeah, so our images came from the COCO data set. COCO is a collection of images with labels. That means that it has, for each image, it has a bounding box around the objects inside of it and a label of what object is in that bounding box. So for a few reasons, we chose COCO for a few reasons. One, the images are a very high quality, not blurry, and they often have a clear subject. There are many types of objects labeled that we could choose from. That was part of the first steps in our model, choosing which objects in COCO where we're going to train our model to detect. And also, like I mentioned before, it has bounding boxes, and it's not just a bunch of images labeled with what type of objects are in them. Next slide. So to generate the images, as you can see, COCO, this is an example of what it would look like, what like an example would look like in COCO. An image, it's a few boxes with labels. And our process was to crop the images around using these new crops that we have with the label that COCO provided. So from one image, we can get multiple examples. Important thing about the examples we generate, each example, one object in it. We don't want to be generating, we don't want to be generating an image that has broccoli and carrots in it. That's going to come up later, you'll see. Next slide. The classes we chose were, as you can see, these different food classes. The reason we chose this is because COCO had a good amount of images for each one of these classes. And yeah, we ignored any images, any objects that did not have these labels. The first version of our data created examples simply using the bounding boxes that COCO provided. A patch of each image of each object was created. The second version was to create examples based off of using selective search. As Ethan explained above, that's a way of generating many bounding boxes for an image. Our criteria, so we ran that algorithm on the model, and we picked out some of those bounding boxes for each object within the image. We've had a few criteria for which selective search bounding boxes we would choose. For one, they had to completely encompass the bounding box that COCO provided. And two, they couldn't be too much bigger than the COCO bounding boxes. Next slide. Okay, we ran into a big problem early in the process where we were getting very poor results. And we looked at some of the examples and we found that they were pretty low quality. As you can see, this is a sandwich example. This is an example labeled as sandwich, but there's a lot of different types of fruits here. We have tomatoes, maybe some oranges, some pineapples. Furthermore, the object that's the image is labeled as is not the primary object in the image. This is, if you were to ask what's the main object and the main subject of this image, it'd be hard to say there's even one, but it'd be even harder to say that the subject is the sandwiches. You might pick the tomatoes because they're more central. The solution to this was to be more selective with which boxes we chose from selective search. We, first of all, if there was ever an image that had more than just one type of food in it, we did not generate any examples from it. This prevented the possibility of having overlap, having multiple types of foods in one example. Furthermore, when I mentioned before that bounding boxes couldn't be too much bigger than the Cocoa bounding box, we were more strict with that. We required them to be smaller than we had before. Next slide. To distribute the data set, the data sets were, after being generated, uploaded to an S3 bucket for everyone in the team to have access. That's our presentation. That's our project.